Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. Good evening. I'm Yvonne Stapp for Science for the Public. Welcome to our program tonight with our guest, Dr. Ben Weiss. Ben Weiss is an associate professor of planetary sciences and the chair of the program in geology, geochemistry, and geobiology at the Massachusetts Institute of Technology. He received his PhD at the California Institute of Technology and joined MIT. Professor Weiss reconstructs the evolution of bodies in the solar system, planets, moons, asteroids, with emphasis on magnetism. He conducts magnetic studies on rocks from Mars, the Moon, and Earth, and his paleomagnetism lab at MIT is a leader in the development of a technology that makes especially detailed analysis possible. One of his interests, his major interest, is the nature of the Moon's core. He's here tonight to explain the role of the magnetic core and the implications for a scientific understanding of the evolution of our solar system. Dr. Weiss will explain how scientists work through different hypotheses to determine the facts of the Moon's structure and evolution. We'll learn that the Moon did indeed once have a core. We'll learn what kind of core it was and what happened to it. And we'll find out what the development of that core means for the evolution of the solar system. Dr. Weiss, welcome to our program.
Thank you.
And yes, and I'd like to start with, could you please refresh our memories about how the Moon itself formed, and then we can go to the core.
Yeah, so the leading idea, as you can see in this image, is that early in the solar system, soon after the Earth formed, 4.5 billion years ago, a large body the size of Mars, roughly, struck the Earth at a glancing blow and blasted material off the Earth, which then formed a disk around the Earth that slowly accumulated into the Moon. This is the leading idea today. There were lots of other ideas in the past that prior to the Apollo missions, for example, it was once thought that the Moon might have just been another foreign body in the solar system that was flying by the Earth and got caught in the Earth's orbit. And the reason, there are actually a bunch of other ideas too. All of these different scenarios for how the Moon formed make very specific predictions for its initial state and what happened to it afterwards. And in particular, the idea of the Earth being hit by a giant impactor predicts that the early Moon should have been very, very, very hot, perhaps molten throughout. Whereas the idea that the Moon maybe was just captured when it was flying by the Earth could predict potentially a very cold Moon. And so these different models have very specific predictions that we can test by looking at the history of the Moon, basically as it's recorded in its rocks. And in particular, the giant impact order of the Moon, which predicts a hot early Moon, would predict that large volumes of huge oceans of magma essentially on the surface, what we call magma ocean. And when you have such an environment, seas of magma, heavy things will sink, light things will float, and the most cosmically abundant heavy element that can sink is iron. And so a Moon formed by a giant impact is expected to naturally have lots of iron sink out to the center and form a central iron core, analogous to what the Earth has today.
Right. This is the origin of the Moon, okay.
So I don't want to leave the audience, people watching this, with the impression that this is solved, that we know the Moon formed from a giant impact. And in particular, a study just a month or two ago has shown that the Moon, its composition, not only just in terms of elements, but its isotopes. So various flavors of titanium with different amounts of neutrons in the nucleus. If you look at the composition of the Moon, it's identical to the Earth as far as we can tell, and it's titanium isotopic composition. And this goes for a number of other elements and isotopes. And this is actually a problem for the giant impact origin. So, because it's most of the simulations show that the moon should form from material from the impactor, not from the Earth, proto-Earth. And so it's funny that if the moon really did form from a giant impact, you'd think that it would inherit the composition of the thing that hit the Earth,
yes,
which you wouldn't think a priori should be the same composition as the Earth. So all I want to say is that there's some open questions that are major that need to be resolved before we can accept this. And this is why magnetic studies can play a really central role in this. So the giant impact origin of the moon predicts a molten metallic core. And a metal is a great conductor. And if you have conducting liquid that's moving in complicated ways, it can generate a magnetic field. This is the way the Earth's magnetic field is generated, by motion of the liquid metallic, metallic liquid in the Earth's center. And in the case of the Earth, it's powered by the fact that Earth is cooling off. So the core is convecting. It's the same thing that goes on in your lava lamp when you have hot stuff rise and then cool stuff sink. So that is a great way to make magnetic fields, we think. And so the prediction is that the early moon should have generated a large-scale magnetic field like the Earth does today. And yet, the first object to ever leave the Earth's orbit that was man-made, the Luna 1 spacecraft, and I have a picture I can show you of that. Luna 1 was the first spacecraft to leave Earth's orbit. It's a Russian probe. It didn't carry a camera, but it carried a magnetometer. And it was immediately clear in 1959 that the moon does not have a magnetic field today. That if it does have one, it's at least 10,000 times we now know weaker than the Earth. So there's this prediction that the moon should have had a magnetic field, and its complete absence as far as we can tell today. So the thing is, though, that the moon is a small body, and you might expect that it would cool off really quickly, like small bodies do. And so there's reasons to think that maybe it may have generated one in its past. And if we want to know what the field was like in its past, whether it existed or not, how strong it was, you can look at the rock record and investigate whether there's remnant magnetization in rocks that is analogous to what a bar magnet has.
Those rocks could have been delivered by asteroids or something, though, but you're saying no, it's definitely moon rocks as opposed to alien rocks. Is that it?
Well, one cool thing from the Apollo missions, they did find some meteorites in the lunar regolith, actually, that were from asteroids, but they're a very small fraction of what's there.
So you're sure that what you're looking at when you investigate these rocks, they're definitely lunar, and then the magnetism will reflect its ancient past. And that's a very good source of evidence, perhaps the best, for what the situation was.
Yeah, the chief challenge in doing this is that the moon has had a very intense history of impacts. You know, all you need to do is look at the lunar surface to see that thing has been busted up repeatedly over and over again for billions of years. And if you look at the rocks that were brought back from the moon, most of them are a mess, especially the ones that are older than 3.9 billion years ago. They're basically cemented angular fragments of pre-existing rocks that were broken up by impacts and basically stuck back together. And if you look at some of these rocks, we call these things breccias. You look at individual so-called clasts, individual rocks within this broken up assemblage, they themselves are little breccias. So the precursor rocks had already been broken up and reassembled. And then you can go down and look in those and you see 3, sometimes 4th generation of rocks being broken up and reassembled. So these things have had a long history of deformation and intense heat and high pressure. And so it's not clear, and this has been a real challenge since the Apollo missions, how to interpret what we see in these rocks.
Okay. Is it a little different from looking at rocks on Earth, which didn't have perhaps that same just endless history of impact in this quite the same way? So it's a little easier to study the rocks on Earth, and that's why you get these different theories, I guess, hypotheses for whether it had a magnetic core or not. What would the magnetic core do for the moon if it had a molten magnetic core originally? What would that do for it as a body?
Okay, so we've said that the implication of a giant impact origin of the moon is that there would be a core that formed. Now, it's been an open question in lunar science until the last few years whether the moon has a core at all.
Yeah.
If it does have a core, it's very small compared to the body compared to the Earth's core, okay? So if you can show that the ancient moon generated a magnetic field, then by implication, you can say that there was a core there. So that's the very first very important piece of information you can establish if you can see that it generated a magnetic field. And then you can tell something about how that magnetic field is generated, potentially. And this is actually an interesting question that has nothing to do, in a way, directly with the origin of the moon. It's a basic physics question. How do bodies generate magnetic fields?
Yeah.
We think we understand that for the Earth, although the funny thing is, we didn't understand it until really the 1950s. So this is after the era of quantum mechanics. Only then was there started to be a good understanding of how classically, without any kind of quantum mechanical relativistic effects, motion of a liquid conductor can generate a magnetic field. It's a very hard problem. So it actually is so hard that Einstein even suggested in the 30s that maybe the Earth's magnetic field was generated by the fact that the protons and electrons don't have the exact same charge. As we know today, we think they do have the same charge. But if there was 1 part in 10 to the minus 17 difference in the charge between the proton and the electron, you add up all the protons and electrons on the Earth, and then you take the Earth's spin rate, that would be enough to generate the Earth's magnetic field, actually. So there were some really wild and interesting ideas that were put forth not too long ago by very smart people to explain the Earth's magnetic field. And as I said, only in the start of the 50s did we begin to really understand that it's a purely classical physical phenomena related to what we call induction, basically motion of a conducting liquid. So the moon, which is much smaller than the Earth, it's 1,700 kilometers in radius. The Earth is 6,400 kilometers in radius. If it did generate a magnetic field, it would be one of the smallest bodies known anywhere to do so.
Okay.
And it turns out that is extremely hard to understand how it could do it, even if it did have a molten core. And so it turns out that, as you will see, lunar rocks do appear to be magnetized, and relatively young lunar rocks do. And not only that, but they're very strongly magnetized compared to what we might think. So what we are starting to see is that there was a lunar magnetic field, and it lasted very long into lunar history, long after you think the moon should have cooled off and convection stopped. And not only that, but the field is very strong. So the moon is like almost a new venue for studying the physics of magnetic field generation in small objects in the universe, essentially.
Because it's rare.
Yeah, so it's
you
the
need
smallest,
a big body to do that.
That's right. It's much easier to do this in big bodies. And so this is challenging our basic understanding of how planets can generate magnetic fields in the first place. Because the moon, at least at first glance, seems to be in the regime that you think couldn't do what it seems to be doing, essentially.
Yes. Also, I'm not absolutely sure about this, but was the moon closer to the Earth earlier in its history? Now, if the moon at that time had a magnetic field and the Earth had a magnetic field, does this affect their relationship at all? And
it's a great question. So one of the first things they found out when they started to see that these rocks were magnetized, one of the first questions they asked is maybe they were magnetized by the Earth.
Yes.
So it turns out that doesn't work if the Earth field was even remotely like it is today. So the moon used to be a lot closer to the Earth. It evolved, its orbit has evolved outwards. So if you put the moon as close as you possibly can put it to the Earth, so if you put it too close to the Earth will tear it apart, basically, because of what we call tidal effects. The gravity of the Earth on the near side of the moon is weaker than the gravity on the far side of the moon. And so that leads to a kind of a pull, and it will actually tear it to pieces if you bring it.
It tears the moon to pieces.
Yes, if you put it too close. And so that's the closest we could have put the Earth to the moon, and yet the field's still not strong enough to explain the very strong magnetic fields that we're inferring to be on the Earth. So we really think the magnetic fields are associated with the moon. Now, another idea has been, and I can show a picture for this. So we've seen that the lunar rocks are magnetized by studying them in our laboratory. The other thing that's been discovered, particularly in the late 90s with the Lunar Prospector spacecraft, which orbited the moon and had a magnetometer, is that it confirmed that while certainly the moon today has no large-scale global magnetic field with a north and a south pole, that the lunar crust, the rocks on the surface on large scales, are magnetized. And we can see weak fields coming out of the crust. So this is essentially remnant magnetization in the crust. And the weird thing is, if you make a map of this remnant magnetization, which you can see here, the red and yellow areas are, so this is the whole lunar surface. The red and yellow areas are strong magnetic fields. The blue and purple are weak, okay? And the white circles show the outlines of the 15 most recent large impact craters on the moon, okay? Now the black circles show the exact opposite side of the moon from those white circles. So each white circle has its own black circle. That we call that the antipode. The weird thing is, if you take the 4 out of the 5 most recent craters that formed on the moon, and you look at the opposite side, shown by these black circles, then you see basically that there's strong magnetic anomalies there. There seems to be strong magnetization associated with these craters. And so that led people to speculate that maybe all this evidence for ancient magnetic fields that we see in rocks from the moon has absolutely nothing at all to do with generation of a magnetic field in the core. That maybe is just related to some superficial phenomenon like an impact, which we know melts rock. Not only does it melt rock, it creates vapor, it creates plasma, ionized fluid. And plasmas are awesome conductors. And they're fluids, just like what's in the center of the moon. And so the idea was that maybe these impacts are transiently generating magnetic fields. And they're magnetizing the lunar rocks, and they have nothing to do at all with a core. And so this has been the alternative hypothesis that the most challenged the idea of a dynamo, a core magnetic field. And it's been what's been debated for the last few decades, and what my group's tried to address directly.
I know that your group has, I guess, won the day on this now, but I am aware, and I hope that people can understand there were really two conflicting views here. And I was going to ask you if you could tell us how this emerged, that gradually, you've already made a case, but gradually you can do away with this explanation of that, but for a while things are kind of equal, right? That you have real competing hypotheses because you don't have a way to definitively settle the issue, but you think you have, and I know that you have an advantage with that.
Well, I would say I came into this relatively recently, and so these two hypotheses were there, and so I didn't have I just wanted to know what the answer was, as most scientists do. So if it turned out that it was just impacts, then we have a fundamentally new way of generating magnetic fields in the solar system that might be more common than what we think of as the typical way. And so that would have been an interesting discovery. Of course, it would have meant that we can't use this record to infer the history and the origin of the moon. So, there were these two ideas, and what we realized when we came into this, it was maybe about 5 years ago we started working on this, is that there's actually a way to distinguish between magnetic fields generated by the core versus magnetic fields generated by impacts.
Is that something recent that you could make that distinction? Just curious.
Yeah,
because that seemed to be a problem.
Yes, because they both, how do you tell the difference is the question, right? And what we realize is the major difference between these two processes is that impacts from fields last a very short time because the plasma from the impact just dissipates it. Whereas a dynamo lasts, for the Earth in this case, the Earth's magnetic field, as far as we know, the oldest rocks that we look at, 3.5 billion years old, they're magnetized. So dynamos can last a very long time. And so what we decided to do is go and measure rocks that we know cooled very slowly on the moon. So the way a rock becomes magnetized is, in this case, if it cools in the presence of a magnetic field from a high temperature. And then it locks in the little electrons in the rock which are spinning. They're like little bar magnets themselves. They'll rotate just like your compass needle rotates toward the North Pole. They'll rotate in the rock and align themselves with the background magnetic field. And then when the rock cools down, they're frozen in place, even if that magnetic field goes away.
Okay, yes.
So the thing is, some rocks that cool really quickly could lock in all of their electrons and point it toward the field in a very short time. And if there happens to be a short-lived magnetic field at that same time from an impact, then it'll become magnetized. But what about a rock that cools really, really slowly? Most of its electrons will be cooling. Basically, the rock will cool when there's no field present whatsoever, unless it's a long-lived magnetic field. So we measured a bunch of rocks that we knew cooled really slowly compared to the lifetime of any possible impact fields. And they're all very nicely magnetized, the ones we've looked at. So a second problem has nothing to do with the impacts, and this has also confounded a lot of people who worked on this problem. The first one, of course, as I just said, is that even if you see magnetization, it might have nothing to do with the core. The second problem is, compared to Earth rocks, lunar rocks are lousy magnetic recorders. They have really low fidelity recording properties. They're like 8-track tapes to Earth rocks, which are like, DVDs essentially. So even if you try to take many of these lunar rocks in the laboratory and you heat it up and you cool it in a nice field, keep it steady, it still can't become magnetized, or it gets a really weird record that just is hard to interpret. So what we had to do is look through the lunar rock collection, and there's 380 kilograms of material that were brought back by Apollo.
Whole truckload.
And find basically the needles in the haystack that happen to be good magnetic recording devices, and then really focus on those. And that's the other thing we've done, I think, that's important.
I have to ask this for our audience here. I know that one of the, like stars, they have these names yay long with lots of numbers and stuff. It's like like a password or something like that. But you've been studying one that's quite famous. Is that correct? This
Yes.
R something or other, something or other.
Yeah, I can show you a picture of one of these things.
Thank you. We'd really like to see that.
Here's one.
And why is that thing so significant?
So this is Apollo 17 rock. It's called 76535.
There you are, I got a number.
The 7 you can understand because it means from Apollo 17.
Oh,
so every
got that,
Apollo
okay.
17 rock. And some people call this the prettiest lunar rock because it's basically this it's very coarse grained. They're big crystals, like several millimeters or larger, sometimes up to a centimeter in some cases. Big jewel-like crystals of plagioclase and olivine. That's 2 common minerals we see on the Earth as well. And it's a sample of the deep, deep lunar crust. We think it came from tens of kilometers deep into the moon and was ejected by some gigantic impact 4.2 billion years ago. So this rock is older than any rock we have from the Earth. And somehow it lived through this incredibly violent time in lunar history when the surface was being repeatedly hit by huge impactors. This thing somehow escaped all of this trauma and came to us the present day without being affected at all by any kind of high pressure effects or deformation. And it cooled really, really slowly, much, much slower, tens of thousands of years or longer. And these impact generated fields, if they happen at all, we think would last at most a day. Okay, so this is the first rock we studied. And the other thing that's interesting about this one, and this is the reason we went after it, is that because it's basically the oldest well-preserved lunar rock. So it tells us about the earliest history of any magnetism on the moon that right now we can access with the Apollo sample suite. Now there are ideas of going back to the moon and getting older samples, and we're hoping that happens someday, robotically actually.
We hope it does happen, right?
But in the meantime, this is the oldest thing that we have. And it's so old that it formed when the moon its core could have been convecting. So the moon, if it formed hot, and we had the molten moon, and the core was moving to a lot of lava lamp style convection, this thing formed at a time when that could have still been going on. Now, one of the big problems with understanding the idea that the moon generated its own magnetic field is that a lot of models suggest that this early period of convection in the core would have shut off after this time. And so we didn't want to measure any samples to start with that would have formed after this early period when the moon could have generated a field. We wanted to try one that would be simple, which was formed when there should have been a field, the way we expect it to be. And this one indeed confirmed that was the case. So the second sample we measured is an Apollo 11 sample. This is 100020. This sample, that's actually a picture of it at Johnson Space Center in a kind of, it's in a nitrogen cabinet there. So you see these discs on the right there. You basically handle these things with a glove box.
Yes, I see. Okay.
Yes, so this one, go ahead, sorry.
I'm sorry, I just wanted to know what the brick was.
That's a 1-inch cube.
To give you an idea of the size of it.
Yeah, and also that you'll see it has a north, south, east, west on it. So they're all oriented. They've documented how they pick these things up on the lunar surface and stuff like that. So this one is 500 million years younger than the previous sample we studied. This sample is so much younger. It's still older than just about every rock we have on the Earth.
Yeah.
But it's so much younger that it formed at a time when we think it's hard for the moon's core to have been convecting, because the moon is so small it should have cooled off relatively quickly. So people who've looked at this problem have argued that the moon's core should not have been moving as a result of convection at this time. So if this thing is magnetized, then it requires a major change in understanding of how fields are generated or what was happening in the core. And it turns out it's spectacularly magnetized. And it implies that there were very strong fields of the moon, basically equal to the strength of the Earth's field today, 3.7 billion years ago. And again, it's slowly cooled enough that it can't be from impacts. It has to be from some kind of long-lived source, like a core dynamo.
When you look at this unexpectedly, counterintuitively, and everything else, it continues this convection period. What would be the answer to that? We don't have an analogy, is that right, that you know of in the solar system, another small body like that continues this convection of this core, this kind of a core over
that late in history
period.
Yeah, so other things my group have worked on are studying asteroids.
Yes, I know.
We do think that we've discovered that asteroids probably generated magnetic fields too, but they didn't last very long, just for the reasons that we were just discussing. They cool off really quickly. So this is very long compared to what we think a body as small as the moon. Small bodies have high surface area to volume ratios. Okay, so the requirement for magnetic field generation is that you have motion of a conducting fluid. No one said what causes that motion. It just needs to be moving. And as I said, in the Earth, it's because of cooling of the Earth. So if you could do this mechanically, then maybe you could have a magnetic field generated later in lunar history. And this was the subject of 2 papers, really important papers, that were published early this year. So a big problem in understanding lunar magnetism is how you get this late dynamo. And what these guys argued is that if you shake up the core somehow, physically, mechanically, then you could actually generate a late magnetic field. And the 2 ideas that were proposed, one was that imagine you hit the moon with a large body, and you hit it as a glancing blow, and then you're hitting the outside solid part of the moon. But if there's a molten interior, like the core, then you'll move the outside with respect to that liquid center, and actually thereby stir it up because of friction on the liquid. The same way a blender essentially stirs up a fluid. And so they showed that if you happen to have a rock that cools around the time of an impact like this, then you could actually have a core dynamo magnetic field magnetizing it. So this is different from the plasma idea. Very different, because the impact-produced plasmas are a superficial phenomena that last a day. Here we're talking about making the core make a magnetic field by stirring it up from an impact. So that's the first idea. The problem with that is that there weren't any big impacts after about 3.85 billion years ago, capable of doing this.
I see.
And this thing is 150 million years younger.
Okay.
So this leaves the other idea, which is that the moon, even today, its core is spinning, its mantle its solid outer part is spinning. Today, even today, the moon's core is partially liquid, which is a surprise to some people, actually. So it turns out that the tilt of the solid part of the core, like the spin pole, it's tilted with respect to the core. So if you have the core like this, actually I have a picture I can show you. Much better than my thumbs.
Yes, right. But we were impressed with the thumbs, right.
So here's a picture.
That is better.
So here you see the gray, the kind of, should I be looking at this or?
Yeah,
okay.
that's fine.
Yeah, so you see the outer kind of greenish brown mantle, the solid part of the core. Then you see this red liquid core center where the metal is. The core is spinning with its north spin pole along that big vertical arrow right in the middle. Now the mantle is also spinning, but it's tilted with respect to the core. And not only that, not only is it tilted, but it precesses like a top. Spinning, but also it wobbles.
Right, right.
Okay, and so what's happening is that the mantle, the hard part of the outside of the moon, is actually moving again with respect to the liquid core. So if that's rapid enough, then again that will stir up the core. Okay. Because the mantle is moving with respect to it.
All right.
And this was much more extreme early in lunar history. So when the moon was closer to the Earth, this was the angle between them, which is today only 1.5 degrees. It's a very small amount. They're almost perfectly aligned. Back then, it was much larger, and they were spinning different, moving with respect to each other much more rapidly. And as the moon's orbit evolved outwards from the Earth, that's gradually slowed down the relative motion between them. And what this other study showed is that this dumped so much power, so much energy into the core that it could stir it up for billions of years, maybe lasting even to 2.5, 3 billion years ago.
Is that related to like the Earth sort of shoving it, or is that a part of this?
It's the Earth's gravity, in fact, that's causing the precession.
Okay.
So without the Earth's gravity, this would not happen.
It wouldn't be happening then.
Yes,
right,
so you can think of this as the
it's a
Earth.
relation.
Yes. It requires a weight to be pulled on the moon.
Yeah.
It's slightly complicated to explain, but it's essential. It requires Earth's gravity. So in a sense, the Earth is doing this to the moon.
Okay. Now, in your lab, you resolve all of these issues, right?
We're working on it.
Everybody lives happily ever after at the end of this. I know that there are a number of really big labs working on this stuff. And so you have a technology. I wonder if you're ready to tell us about that, or did you have something else you want to tell us about, just the coreness of the moon before that? But I'd like to talk about Squid.
Okay, squids, yes. So we are using an instrument called superconducting quantum interference device, which is basically a magnetometer. It measures magnetic fields. And lunar rocks, another problem that was really held this back from the field back for a while, is that lunar rocks are extremely non-magnetic. They have very little metal in them, which is what's carrying the magnetization. And the reason for that is that basically all of the way the moon, we think, formed, as I said, by a giant impact, that the moon basically formed from the rocky outer part of the impactor that hit the Earth. So the moon didn't get the metal from the impactor that hit the Earth. So almost all of the metal went into the Earth's core. The moon ended up with a very small amount of metal. And that's one reason why the moon's core seems to be so small, we think. And also it means the lunar rocks have very little material in them by which you could record magnetic fields.
And certainly no iron then.
A little, just the tiniest amount, you know. Yeah. I mean, you cannot take a lunar rock and stick it to your refrigerator.
Don't even try, right?
It's just, they're not magnetic. So we need an extremely sensitive magnetometer to see this very weak magnetization. Right. In fact, some of these lunar rocks are some of the most weakly magnetic materials we know of in the solar system, actually. So particularly the white part of the moon, the highlands, what we call it's made out of anorthosite. So you need a very sensitive magnetometer, and the best way to get high sensitivity is to use something very, very cold, because then basically the noise, which is from motion, ultimately of electrons and stuff, the thermal noise is lower. So what a superconducting quantum interference device, or SQUID magnetometer, is essentially is a bunch of coils that are held at minus 269 degrees Celsius, and you basically lower the sample into the middle of these things. And the way any magnetometer typically works is if you lower something into it, basically that'll induce a current into the loops. And if they're superconducting, they're extremely sensitive. So those superconducting magnetometers only really started to be available in the early 80s, and they've been developed to much higher precision and accuracy and sensitivity today. And so almost all of the Apollo era studies did not benefit from this insensitivity.
At that beginning, especially.
Yeah.
So therefore, you have a lot of hypotheses, competing hypotheses.
Yeah.
But now you can resolve a lot of that. Likewise, I assume with like asteroids, would you have a similar kind of a problem with analyzing this kind of rock? I'm not sure.
Absolutely, yeah.
Okay.
Asteroids also, if you look at, they look pretty beaten up. And
Do they ever? Yes, right.
And so we've had to again find rocks that were pristine, somehow survived from the earliest solar systems.
Yeah.
And they're extremely rare on asteroids. And even if you find ones that are pristine, most of them are lousy magnetic recording devices, just like the moon.
Yeah.
So again, it's a matter of needles in the haystack.
Right. Where do you go from here? Do you what's the sort of the next thing that you're doing with this?
Okay, so then the question is, when did the field turn off? And that tells us what's interesting about that is that if it's true that the moon's field was generated by this precession, motion of the mantle with respect to the core, that, as I said, should decrease with time as the moon moves away from the Earth. And the rate at which that happened is something that no one really knows very well. So when was the moon at a certain position relative to the Earth in the past? This has lots of really interesting implications because the Earth's spin rate is changing in time. So not only is the moon's orbit changing, but the Earth's spin rate is also changing in time. So days were very different length in the past, billions of years ago. So this has implications for the Earth as well. And it also tells us something about, without getting into too much detail, basically the rate at which the moon moves away from the Earth tells us about the large-scale internal structure of the Earth. It depends on that.
Yeah.
So we'd really like to know how rapidly the moon moved away from the Earth. It says a lot about the evolution of the two bodies and their spin rates and their thermal evolution in time. So if we could say, what if we could turn the problem around? We say, guess what? The field turned off at X billion years ago. Then they can see how much energy, basically that would mean that the moon had moved away to a far enough distance that the precession-driven magnetic field turned off.
Yes.
So then you could back out exactly when that happened, when that distance from the Earth actually happened. So that's,
and you can reconstruct quite a history, a chunk of the solar history that way, solar system history like that. So that answers, that potentially will answer a whole range of questions, I imagine.
Nothing to do with the magnetic field at all.
Exactly, but you just are able to reconstruct based on just that.
Yes.
In terms of the solar system, it seems to me that the work that you do, because you cover a lot of ground, not just geomagnetism, but you're interested in origins of life, a whole bunch of things here, and we're finding that we're more and more in a period of scientific convergence. So when you started your studies, you may have specialized in one thing, but already you direct a program that covers a huge expanse of things, and your students presumably are training across fields now. So it's a rather demanding thing to be a Renaissance person now. You have to know so much, but I think of you as thinking very systemically. So when you look at the moon, you're not really looking just at the moon, but rather at a system, a solar system. So if X is true here, it's going to tell us something about the natural evolution. Is that the case?
Yes. So The moon is the moon is a central role in planetary science because it's so much better studied than any other object outside the Earth. We've been there, we have samples, we've observed it from the Earth for centuries, we've had numerous spacecraft visit it, and so a lot of our basic understanding of planetary science is anchored to our understanding of the moon. I mean, a perfect example of that is how we tell time on planets. So if we look at Mars, we see, places that are older have more craters, and places that are younger have fewer craters. It's just intuitively obvious. But the way we can calibrate that, so how old is the question, is because we've actually been to the moon, where we see the places with more craters are old, and we actually brought samples back from there and can date them in our laboratory using radiometric dating. So we actually can directly date these surfaces, and so that calibration is then basically transferred to other planets. So we now have reconstructed the history and rate of impacts on the planetary surfaces from studying the moon. Now, in the context of lunar magnetism, again, we have samples of the moon, more samples than we have of any other planetary body. We have something like several dozen Martian meteorites, naturally transferred from Mars to Earth. And actually, this is what I did my PhD on.
Oh, it was Mars.
Is that we showed that even though Mars today does not have a magnetic field, it did have one in the past, actually. And we can tell that by looking at some of these meteorites. But we have no idea where they came from on Mars. No one went there and picked them up. They were just blasted off randomly and wander around in space. And we don't have nearly the kind of collection that we have from the moon. So if we can show that the moon was magnetized by this totally new type of power source, precession, not from lava lamp style convection, then we've basically provided evidence for this new way of generating magnetic fields that could potentially go on elsewhere in the solar system.
Right,
so
around some of those interesting
there
moons
are moons
out there.
all over the place.
Yeah, right.
So this is a natural, these ideas can then potentially be extended to other bodies.
Right. Okay, so there's some underlying laws that you're looking for in this process. It is very interesting. I think most of us are not aware of how crucial the moon is, and the core in particular, how much this tells you. One more thing, and you said the core is still liquid in the moon. It's small but liquid. How do you know? Or is it viscous or liquid, or you can pour it?
Yeah, definitely.
But how do you know that? You can confirm that right now? Because I'm asking because there were these theories that actually the moon does not have layers, it doesn't have a core, and I even saw that in a documentary. I think I wrote to you, I said, straighten this out. It's fairly recent. So these theories were still present.
Again, this is one of my favorite experiments that's been done for the moon that answers this question. So I have a picture for you. Here we go. So this is the most bang for your buck science experiment that I can think of. The Apollo missions, they brought these retroreflectors. They're basically little arrays of mirrors, and it's basically 3 planar mirrors in like the edge of a cube, a corner cube. So when you have that configuration, and this basically shows you an array of a bunch of them, if you shine a laser at that from any direction, it will always bounce back to you perfectly.
Yeah.
So they put these on the moon in the late 1960s and early 70s, and basically ever since, people have been firing lasers at these things.
Yeah.
And what they do is they measure how long it takes for the laser to come back.
Okay.
And what they get by that is a very precise measurement of the exact position of each of these retroreflectors. And there's even one on one of the Soviet rovers that they just started using again. Yeah. So we have these all over the moon. And so what we can actually do from this is see the moon wobbling in time today. Okay?
Right.
And the cool thing about this experiment, which has no working parts or motors or power source, just sits there, okay, is that our ability to time precisely how long it takes for the laser to get there and back has gotten better and better and better over the last few decades, because the technology on Earth has been proved, and the ability to to power these lasers. This experiment, now they're able to do this with incredible precision, better than millimeter precision. So what we can now see is basically the motion of the liquid, of the motion of the moon as it wobbles in time. And from doing that, you can actually infer that there must be some liquid which is dragging essentially on the outer solid part of the moon, because it's slightly misoriented for what it would be if the entire moon was solid. There's something that it's dragging on.
I see.
And so this data, which is incredible, is really since around 2001 clearly demonstrated that the moon today has a partially molten outer core. So what I mean by that is probably has a solid inner core. The Earth has a solid inner core too, and that's surrounded by an outer liquid layer. Okay, so what about the solid inner layer, you might ask then? I think I might have a slide for this too. Oh yes, great.
Oh, great.
So this is no longer future, although it says. This is the GRAIL mission, which is the Gravity Interior Laboratory mission. This is 2 spacecraft flying information which arrived at the moon a few months ago. And what they are doing is firing lasers at each other and then communicating back toward the Earth.
See that?
And so this is a mission being led by one of my colleagues at MIT, Maria Zuber.
Yes.
And what this will do is measure the gravity field of the moon to unbelievably high precision that will far exceed what's been done before, by basically watching the 2 spacecraft be perturbed as they fly over structures on the moon. They will get a gravity field map of the lunar gravity field. So what does this mean for the context of what we're talking about? So I said before how the mantle is moving with respect to the liquid core. Now we just talked about how the liquid core itself is not homogeneous. There's actually a solid center. Okay, here's the cool thing. That solid center should be wobbling with respect to the liquid outer layer. And it should be wobbling differently from the mantle. So just imagine a solid thing wobbling, liquid layer, and then another wobbling thing inside. And if you have good enough measurements over time, you could see the change in the gravity from that wobble. So one of the goals of this mission is to actually, for the first time, detect a solid inner core for the moon as well. So that's something that we might hear about in the next year or so.
Amazing. This is the greatest age to be alive for space science, isn't it? There's just so much going on now. And we have just a few minutes left, I'm afraid. And is there anything else that you would like to tell us or show us before?
No, that's good.
Okay. Then I guess we will leave it there for the time being so the audience has time to ask you some questions. And we have a few minutes left. We'll get a few questions in. Dr. Weiss, would you try to repeat the question? Make your question kind of quick. When we stop, you can continue to ask questions, but we can only get a few probably on the tape. I'm sorry. But go right ahead. And before we start, thank you very much
for
that. Really appreciate it. And the floor is yours. There. Go right ahead.
So the question is, has the moon's size changed in time? Good. As far as we can tell, the moon's size has pretty much been fixed for most of its history, and we can tell that just by looking at the surface. Most of the surface is super, super old, so there hasn't been anything that's really been added to it since. Now, the moon's shape has certainly changed in time. In fact, it's a little bit oblate. It's got it's a little fat at the equator, and this is a subtle thing that's confused a lot of people, but it's not because it's spinning. So the Earth has a little fat kind of equator too, because it's spinning, it kind of falls out. The moon is far too cold and solid for this to be causing its fat equator. And so it's basically frozen in from an earlier time when the moon was mushier, essentially, and probably was spinning faster. So it does record an early period when it was probably more mushy and spinning probably a little faster, and that's kind of it's been frozen in kind of almost like a disc shape.
Very interesting. Can you see? I'm not sure you
yes,
see
sure.
him.
Why is the moon going away from the Earth? Like, why is it moving farther away from the Earth?
Yeah, so good question. Why is the moon moving away from the Earth? So it's tides. So by that I mean, if you have the moon, the near side is closer to the Earth than the far side. So the near side is experiencing a greater gravitational force than the far side. And what that does is it actually turns the moon into a football. Okay? Now, imagine the moon's spinning, and it's a football. But because it takes it, as it spins, that the football end is always deflected a little bit away from pointing directly toward the Earth, because it takes it a little while for it to relax. So you have a football, and basically the near side of the football is being pulled by stronger gravity than the far side. So it actually pulls it wants to keep the football aligned, and that slows down its spin rate. It's because the Earth, to say it again, the Earth turns the moon into a football because the gravity is stronger on the near side than the far side. And then the Earth's gravity acts on the two ends of the football to align it, and that's actually changing the spin rate when you do it that way. So it happens basically in many, many moon systems all throughout the solar system. You see many moons around Jupiter. They only keep one face facing.
That's right, and that's why that was
Yep,
part of
that's
it.
the reason.
Very interesting that always wondered why the one face, but now we see, and a lot of wobble and stuff. More questions?
Oh, okay.
The moon is moving away from the Earth now. Now, has that been through history? Does it move out, get so far where it neutralizes and starts moving back?
Okay, yes. So it'll keep moving out forever, but the rate at which it will move out will slow down with time. Okay, and so let me say one other interesting thing about this, which has nothing to do with the moon, but it's fun. So if the moon had formed within a certain distance, it would have actually moved in. Okay? So it depends where one of these objects form, whether they move out or they move in. So an example of something that started in too close is one of Mars's moon, Phobos. And this is an interesting story that goes back to the 60s. Before we had pictures of Phobos, we had astronomical observations that Phobos' orbit was slowly decreasing in time. And Carl Sagan was writing a book with a Russian person that he'd never really met, because it was during the Cold War era. They wrote this book, which is called Intelligent Life in the Universe. I encourage you all to take a look at this book if you haven't already. On my edition, there's a big picture of an eye in a galaxy looking out at you. It's very bizarre. So if you look at this book, there's each paragraph, or every two paragraphs, is written by the other person, and they have different fonts for the Russian scientist versus Carl Sagan. So they did this all by correspondence. It's hundreds of pages long, this thing. Okay, anyway, there's a chapter in there called Are the Moons of Mars Artificial Satellites? So they knew that Phobos was falling in, and they're like, how could it be doing that? And they ended up concluding that it was basically a hollow space station left by an ancient Martian dead civilization that was experiencing drag, essentially, in the tenuous Martian atmosphere. So we now know that it's actually because of tidal effects again. And when we first got high-resolution images of this thing, it was clear that it's just an asteroid that was captured by Mars.
It really is ugly, isn't it? Yeah, it's really an ugly thing. I'm afraid that for purposes of recording, we have to stop because we're out of time. But you should feel free to go ahead and ask questions. But I will just say thank you very much now, and we will have to end. But the audience is welcome to ask questions and stay and ask questions. Thank you again.